Hello everyone, this video is going to go over modifying a sample example file that's provided with the FDS installation into a room that could be used to model a fire that was done in real life. Short disclaimer before we get started: the information presented is for educational purposes only. It is believed to be accurate and reliable, but no warranty expressed or implied is offered as to the accuracy of the information. Neither the author nor the publisher assume any responsibility for the use of this information, and the user is obliged to obtain professional guidance for any decisions affecting safety of people or property. Shouldn't use this information solely for life safety and property safety purposes. So I'm going to copy that complete. I didn't read the whole thing word for word, but I'm going to copy that into the description of the video. And once again, that is referenced. It's not a direct copy of the language from the Ignition Handbook, the disclaimer in the Ignition Handbook, but I harp on students that they need to reference where they get ideas they didn't make up themselves, so I reference sort of the guiding disclaimer that was used to create this one. Alright, so we're going to model a fire. Well, we're going to model one room of a burned building. So this is an 8-cell burn building. There's a fire that happened in cell A1, so this cell, and we're going to try to model that cell. We're going to put in a simple fire. We're just going to be a t-squared growth rate fire. It's not going to try to model anything specifically. And we're going to color these sides. We're going to specifically color the individual walls so that we can see which wall we're dealing with. If one wall, the dimensions aren't set quite right, then you can see it, you can tell by color. I find that really useful with students when you have a room full of 30 students and you're trying to get them to code or type in the dimensions for a specific room. If the walls are colored, then I know their blue wall isn't quite right. If something's wrong, or if they're not lining up correctly, we can see which lines to look at. Because when you start looking at these text files, it's hard to distinguish if things aren't identified easily. So what I've done is taken that room and created a top and side view of the room. So we have a top view, and in this view we've identified the lines associated with side A, side B, side C, side D, and the top. And then we have a side view that identifies the windows, and on those views we have the dimensions associated with the different things, with the different obstructions, and then these are holes. You can, we could build this wall out of a variety of obstructions that left a space between them, or we can create a hole. One reason you might want to create a multiple wall structure or multiple piece wall is if you wanted, let's say you wanted the window to disappear. I don't know of a way to have a space there, have a material there when you're cutting a hole. So when I have a window, we'll do in another video I'm planning to make, I add a transparent obstruction in front of the window and have that disappear partway through the simulation. But I can't have it physically where the hole is. I have to have it in front of the hole. Okay, so first thing we're going to do is we are going to copy. We have a room fire. We're going to take this, we're going to open this roomfire.fds file. We're going to save it as a new file, and so I don't have the option to save it as a .fds and I know there's a way to do it, but I don't remember what it is. So I'm gonna call this room fire mod 1, and I might do version 01. Okay, so I'll make another version later, and I'm gonna save it. Then I'm gonna modify this header line. And I need to do a few more things. Our room is a bit taller than the simulation room. So our room is 2.9 meters tall. The burn cells are 2.9 meters tall. So we can't fit that in our simulation here because the domain is only 2.4 meters tall. So we're going to change this and to keep our 10 centimeter grid, we're gonna change this to 3.0. To keep our 10 centimeter grid, we're going to change our spacing to 30, our number of grids to 30. We're going to make this x coordinate negative 0.8, and we're going to change this one to 60 so that our time remains the same, or our grid spacings remain the same. We're going to modify this timeline to be t equals 0, and what this is going to do is when we run our simulation, so that we can look at the geometry without having to start the program, hit Control-C and stop it after it starts running, this should automatically set up the geometry in the smoke view file and then stop by itself. So that allows a quick check of the geometry. So then I'm going to delete all of the stuff that I don't need. So we're not going to deal with the material properties. I'm just going to have a burner. I'm not going to have the materials try to burn. So you do need a react line. That's an important bit you can't really get rid of. But I'm going to get rid of their burner. This is another reason I think somebody messed with this model, is because this line, as the other ones I talked about in the last video, doesn't have an ampersand. So I think it might have been changed by me or someone else. I don't remember. But I'm going to get rid of, I'm not going to deal with the foam, the plastic, and we want to be aware of these are fabricated properties, right? They're not real properties. You don't want to run a model using these properties and go to court and try to justify, well, they came with the program. Clearly they must be accurate. That's not what you want to do. So the more complicated you make your model, the more you have to lock down your parameters and make sure that what you put in is actually correct. So I'm going to get rid of the material ID, the service IDs. I'm not going to use them. And we're going to create our own vent lines, obstructions and vent lines here for the burner, and we're going to put in our own T-squared ramp. So I'm going to keep one obstruction line because I don't want to change it. I'm going to keep one whole line because it gives me the the nomenclature. I'm going to get rid of this because I deleted the carpet. So here's our vents. So they have this YMen service ID is open. I'm going to make all the walls open, or not all the walls, but all of the domain boundaries open except for the X-men, no, the Z-men, so the floor. And so I'm going to start to put in these obstructions. So to put in side A, so this is my front face. And typically I don't use 4 significant digits for room dimensions, but those were the accuracy of the dimensions showed on this plan was 4 significant digits, so we're going to hold with it. But typically, I wouldn't do that in real life. So we're going to go from 0.0000 to 5.0768. So that's the X dimension, the Y dimension 0.000 to 0.1. So that's a 10 centimeter wall thickness. Now if my wall isn't 10 centimeters thick, I'm going to have to change my grid spacing because I can really only have solids that start and stop on a grid spacing. So I'm going to go to 0 to, and I like to keep the number of significant digits for the different obstacles, holes, locations the same so that the dimensions line up. So I can check the X coordinates going down the list of obstructions without having to worry about space changes. And if you haven't memorized the different colors that exist in FDS, you can use your favorite search engine, and there is a wiki that has them all listed out conveniently. So our / will indicate our that it's going to be comments after that. And now I'm going to go ahead and put this door in the front, and then I'm going to check my geometry as it sits. So before I type in the rest of it, and I probably won't type all these in by hand because that would make for a very long video. But when I do it in class, I will go through typing in all the lines directly for this example, so the students type them all in, and then we'll go through it step by step together. And then when we get to the more advanced stuff, I give them the code to copy and paste in, which is what I'm going to do for the fire because I don't want to type in all the ramp lines manually. And luckily there are websites available that will generate the text needed for ramp functions like the one that I'm going to show here. So if I save this, and I go to my command prompt, I don't want to get back to the desktop from the D drive. Alright, so I'm going to back out of that. I have my directory, so I'm working with, it should be a room fire. Oh yeah, this is just our room fire version 01. And I should be able to do FDS room fire underscore mod1 version 1 dot txt. So we can see we got setup only and it stopped automatically, which is pretty cool. And if I'm going to open my smoke view, and I can see I have my one orange wall. I still have my thermocouples from the previous example, and I have my door. So I can type in the next obstruction. You can type it in manually, or oftentimes I will copy a previous line, because a lot of them, you know, the line is very similar. So I'm just reading off here. .3696 02.9. This color is navy. Line B. .1 to 4.3696 to 4.4696. Oh, no, I did something wrong. So this is going to be side C. 0 to 5. 4.3. Okay. So this one goes here. This goes 4. And this one goes back to being 0. And if I save this, go to my command prompt, hit the up arrow, it'll automatically load the last command that was given. And then I can go to, if I'd left my FDS file open, I could reload it. So we'll see if we can do that. So now I forgot to change the color. This is going to be side C. It's going to be yellow. So if I save this, I go back here, I should be able to reload thought it would let me it'll let you reload sort of your it'll let you reload the smoke file, the temperature, slice files, etc. as the simulation runs, but it looks like it won't let you just reload the geometry. I think there should be a way. I'm not thinking of it right now. Okay, maybe. Did I not save it before I ran it? That's possible. All right, we're working through our problem solving in FDS as we go through. So I'm going to leave this video open and see if the geometry changes when I reload after I add the next one. All right, this is taking a bit too long, so I'm going to go. I've already done this for this. Where's my .txt file? I don't see it. Maybe I copied it out of there. Oh, there it is. Okay, I'm just going to go with this one. So I can copy, I need side D on the top, put those in. I need side A window. I'm going to have to manually type in side B because I don't have it in this simulation. All right, so side B is going to be 0, 0 to 1. So that's just the thickness of the wall. One meter wide and 1 meter tall. Okay. So experiment. If we reload this, will the geometry load? Still no. Interesting. Oh. Wait. I need to run it first. It is getting late in the evening, not gonna lie. Still not reloading. Let me see. All right, that's unfortunate. Okay, so we have our two windows, we have our door. Now we want to change, we need to input our fire. I really thought you could reload the geometry. Maybe there's a way. If you find it, you can post it in the comments if you like. So we need an obstruction to place our vent, and then a vent that's going to serve as our fire. So this is going to be a 1 meter square object. And then, so we've identified the surface ID, and we're going to create lines. We're going to put in lines and make this surface ID a t-squared function. It's going to peak out at 1 megawatt, 1,000 kilowatts. It's going to be colored red. It's going to have the ID of fire, so that's going to match up here. And then our ramp is called t-squared, and then our ramp ID is matches from here to there, and then you identify your time and the fraction that you want to use. So we're going to start out at 0, and we're going to ramp up over 140 seconds. So this line of code was generated by a website created by Dr. Overholt. Now he's moved his code has been moved to, I have it linked in this other second example I want to do. It's linked to the utfireresearch.com ramp calculator website. So it used to be on Dr. Overholt's website. Now it's moved to this other source. It's still there. So it's quite useful. So we deleted the extra furniture, we put in the vents, so we can save, and now we would want to change this time back up to however long we wanted it to run. You know, if we only wanted it to run as long as the ramp was going, then we're going to increase. It should hold after this. It should continue at this rate after 140 seconds. So if we do this here, now it's going to think about it. The screen capture is probably taking up. This isn't the fastest laptop I have to work with, but it's the one I'm using today. So we can see our model is running, and so if I wanted to stop it, I could hit Control C, and if I go to this modified room fire, this should be where I ran the simulation before. So we have a room, we have our fire, we have our burner. We can load our smoke. Now, and we can see that it's exiting the simulation there. And so I only ran this for, I guess, about 95 seconds. So now seeing if, let's say we put in, we might unload the smoke and be interested in looking at the temperatures inside. It's a bit difficult to see, you know, what's going on. So we might change the obstacles to outline only, and then we can see inside much clearer. This speed's a little too fast for me, so I might change the max frame rate to 10 frames a second. So I didn't add any other slice files. So maybe I want to look at the heat release rate per unit area. I can click on this and move it myself. I don't know what's going to happen if I do the boundary file with our hidden. I guess it'll show up. So those colors are just the slice files. Okay, what was on my list? So other things. Yes, the grid resolution. So this is a big deal. If you've gotten into CFD at all, everybody knows CFD or grid resolution is a very large deal. There's been a lot of work on verification and validation by a wide variety of people. So I referenced two papers here. One is the Nuclear Regulatory Commission New Reg 1824 that has a discussion of grid resolution. And when we talk about this for FDS, a lot of times you'll see a D star over DX value. And so this D star is known as a characteristic fire diameter. And it's given by this equation here, and these are sample input parameters, not necessarily guaranteed to be correct. But in these papers, there's another paper by McGrattan et al., a bunch of them, that said a D star over DX from 5 to 10 provides favorable results at a moderate computational cost. In this paper, they are ranging it from 4 to 16. And if we look at this website, the UT Fire Research website, they say D star between 4 to 16 accurately resolves fire and virus scenarios based on this New Reg 1824 report results. The user's guide also mentioned, the FDS user's guide also mentions using values ranging between 4 to 16 in a footnote, but I personally haven't gone through this report to verify that these statements are accurate. You know, referencing a second party to what a first party says isn't good practice, but I put it here. I think these are fairly reliable references. But I would recommend you check out this report if you're going to base your professional work on these numbers. So if we look at this 4 to 16 range, and we were to break this down into 3 categories, maybe a coarse, a moderate, and a fine, we could we'd have these 3 scenarios where coarse D star over DX equals 4, moderate D star over DX equals 10, and fine D star over DX equals 16. And this is Dr. Overholt talked about this on his website previously. It looks like that discussion has been removed, but I think it's a reasonable thing to do just to get an idea of what our grid spacing range might look like. So we do want to do, this doesn't excuse you from doing a mesh analysis or a mesh sensitivity study, but it does give you a starting point, in my opinion. So for our example, we might calculate D star, and if we said, all right, our heat release rate is 1,000, then our D star using these input parameters is 0.959, and so that's 9.5 centimeters. This is 9.959 meters. And this is a very sort of crude way to type in these parameters. They should have units, in my opinion. But I didn't do it. So I specifically left it out so I could mention that when you type out equations like this in either a report or a notes for yourself, I think you really want to include units so that you can make sure your units are canceling out and the correct inputs are going into your equations. Now, before I made this video, I was trying to find a reference in the user's guide that says the input temperature is in Kelvin. And since this is, heat trends for like, it should be an absolute temperature scale, but almost all of the other temperature references in the user's guide are in Celsius. I found one other paper that specifies the use of Kelvin in their results, and then several online calculators for D-star specify that the input parameter should be in Kelvin. But I couldn't find a specific output from NIST, a reference from NIST that said T infinity for this equation is Kelvin. But I believe Kelvin is correct. And if you put in Celsius, then the course grid spacing is 70 centimeters, which seems pretty large for me. So I just checked just to see, so we could say we checked. And I don't think that's a reasonable result. So I would, before you go to court and provide these results, I would see if you can find a surefire reference. But, so if we look at based on this, if we look at our results, for a coarse grid spacing, we would start with a 23.9 centimeter grid. What we've done is right around the moderate at a 9.5 centimeters, and then a fine would be 5.99 centimeters. And when I do this in class, I have the students run these two scenarios and compare the results and how long it takes for the two results to be calculated. Just to clarify, according to the user's guide, input files should be built with relatively coarse message and then gradually refined until changes in mesh does not cause an appreciable difference in the results. So that's your mass sensitivity study that we all need to do when we do a CFD type of model. So I believe that is everything I wanted to talk about in this video. And the next one I want to make, I'm going to change some of these devices, put in some different slice files, a sprinkler and some other things, disappearing objects, and have this ramp go up and down. Okay, so I hope you've found this useful and have a good day.